Hello students, welcome everyone, welcome to your favorite channel Vedantu NCERT Solutions, where you get detailed solution of each and every NCERT questions, and we will help you to solve all these questions easily. In this session, we will see how to solve NCERT Miscellaneous question 1 of your exercise relation and function. See children, in the previous exercise 1.1 and 1.2, we have clearly seen how to check the given relation as reflexive, symmetric and transitive, and how to check whether it is an equivalence relation. And in exercise 1.2, we have seen how to check whether the given function is 1, 1 and on 2, and how to conclude that it is a bijective function. Now, in this question, they are telling us that show that the given function, which is defined from a set of real numbers as a domain to a codomain where x belongs to R and it is greater than -1, less than 1. And now the function f of x is given as x divided by 1 plus mod of x. This is a given question. Now we need to check whether R is 1, 1 and onto, and x belongs to R. That is set of real numbers. Now observe this very carefully children. In this question they have given modulus function. So before we solve, let me tell you how to use modulus function when you are simplifying and solving. So whenever you get modulus of x, we can write this as two ways based on the value of x. If x is greater than 0 children, modulus of x can be simply written as x. Why? Because it's positive, modulus have no effect, correct? Modulus of 2 and just 2 has the same value. But if x is less than 0 children, that is x negative, then instead of modulus you can write it as minus x, because x is already negative, minus of minus becomes positive. So it would give the same value as that of the modulus. So modulus of x when x is negative and minus x when x is negative gives you the same value. So modulus of x is written as x when x is greater than 0. It is written as minus x when x is less than 0. If you can understand this, if you know this, then this problem is very, very simple and easy. Now let us check whether the given function is 1, 1. See, in order to check the given function is 1, 1 children, here some conditions we need to see. Because how do we conclude whether the given function is 1, 1? When f of x is equal to f of y, after simplification we should get x equal to y. But we have certain condition, correct? So when f of x is equal to f of y, basically it becomes x divided by 1 plus modulus of x, y divided by 1 plus modulus of y. Until this it is simple. But now when you have modulus of x, we have a condition. First condition, observe this. If you are simplifying, when x is positive and y is negative, we will check what happens in this condition, and y is negative. In this case children, when x is positive and y is negative, observe this very carefully. When x is positive and y is negative, it becomes x plus x divided by 1 plus x, which is equal to y divided by 1 minus y. Why? Because modulus of y when you're writing, if y is negative, instead of modulus what do we write children? Minus y. So in this case, if you're simplifying here, it would become x minus xy, which is equal to xy plus x. Yes children, xy plus y, sorry, it's xy plus y. Yes, so I will write xy plus y here. Okay, now if you're simplifying this, you will get 2xy is equal to x minus y. See children, observe this very carefully. X is positive, y is negative. So what is x minus y? I'll just go to the next slide. We got 2xy is equal to x minus y. See, x is positive, y is negative. Yes or no? If x is positive, y is negative, then your x minus y is positive. Yes or no children? This is positive. But what about your 2xy? 2xy is negative. Correct children? 2xy is negative because y is negative. Yes. In that case, we will write 2xy is not equal to x minus y. Yes children. Next, one more case, when y is negative, y is positive. We have previous case we have taken x positive, y negative. Here let us take the other way around, that is y positive and x negative. What happens in this case also? Let us check, children. Very important, because you will not understand clearly if you don't do for both these cases. Yes, to conclude whether the function is 1, 1 and on 2. Now, if you're taking this way, it becomes x divided by 1 minus x, which is equal to y divided by 1 plus y. Here also, children, observe this very carefully. On simplification, we get 2xy is equal to y minus x, which is not equal again because y minus x is positive, 2xy is negative. So under both these conditions, you can rule it out. That is, f of x, you're not getting f of x is equal to f of y, or you're not getting them as equal terms, correct? So both these cases can be ruled out. Now, what is the cases left? When x and y both positive, x and y both negative. In that condition, when x and y both positive, children, it would become x by 1 plus x is equal to y by 1 plus y, right? In this case, it becomes x plus xy is equal to y plus xy. That means you get x is equal to y. Other way around, when both are negative, children, what happens? X divided by 1 minus x is equal to y divided by 1 minus y. In this case also, you will get x minus xy is equal to y minus xy. In this case also, what are you going to get, children? You will get x equal to y. Yes or no? So in both these conditions, we are getting the given function as what? F of x is equal to f of y only when x is equal to y. That means they both are the same values. In that case, I can write f is 1, 1 function. Yes or no, children? F is a 1, 1 function. And what is the case you're considering? Both x and y has to be positive, both x and y has to be negative, only under these two conditions. Yes. Now let us check whether this function f is on 2. Let us check whether this is on 2. Yes. Now, if a given function is on 2, children, what do we have to prove? When we substitute x in terms of y, f of x, if we get y, then we conclude it to be on 2. Yes or no? In this case, if you take x, x can be taken as y plus 1 by y, correct? Y plus 1 by mod y it becomes, correct? Right, children? Now observe this very carefully, children. If you're going to substitute this, okay, if you're going to substitute this, one case you need to consider when y is negative. Yes, when y is negative and when y is positive, we need to check whether for both the condition f of x is equal to y. Only then we can conclude the given function is on 2. In that case, first observe when y is negative. Let's take this condition first. Okay, when y is negative, under this condition, observe this. When y is negative, I will write f of x is nothing but f of y by 1 plus mod y. Right, children? Yes or no? Y plus 1, y by 1 plus mod y, or f of, we will take it in a simpler way here. We will not write mod because in the function we have mod. So in the place of x, we have y by 1 plus y. Here also we have y by 1 plus y. Let us write it like this. Let's not get confused. Okay. Now, after writing this, observe this, children. What happens here? It becomes y by 1 plus y in the numerator divided by 1 plus modulus of y by 1 plus y. Yes. Now simplify, children. When y is negative, what happens? Your 1 plus y is not affected because you can see the condition under the codomain. It will still be 1 plus y still be positive, correct? So y by 1 plus y divided by, what happens here? 1 minus y divided by 1 plus y, children. Simplify this. What happens? Observe this very carefully. Y divided by 1 plus y, okay, divided by, here it becomes 1 plus y minus y divided by 1 plus y, right, children? 1 plus y and 1 plus y gets cancelled. Y minus y gets cancelled. What is remaining here? You get f of x is equal to y. So what is the conclusion? F of x is equal to y we got when y is negative. Similarly, when y is positive, children, observe this very carefully. When y is positive, in that case also, when you are substituting, what happens here? Tell me, when y is positive. If y is positive, how do you take? When you are simplifying, be very careful here. If y is positive, f of x will be equal to, what happens here also, children? It becomes y in the numerator divided by 1 minus y divided by 1 plus y by 1 minus y, right, children? If y is positive, it will be this case. Yes, in that case also you will get f of x is equal to y. So what is the function? Now your function f is on 2. We can write this function, the given function is on 2 and 1 1. So we write f is 1 1 and on 2. So under both the condition when you're writing, children, that is second condition here, under both the condition, that is when x is positive and x is negative, under both the condition what you're getting, f of x is equal to y. That's the reason we concluded it is on 2. Since it is 1 1, we have already proved this function is 1 1 as well as on 2. I hope this is easy and clear for all of you, children. Yes, in this question they're telling that show that the function whose domain and codomain are the set of real numbers is given by f of x is equal to x cube is an injective function. That means what, children? We need to check whether the given function is injective. That means when f of x is equal to f of y, x should be equal to y, correct? We need to, more or less, we need to prove that the given function is 1 1 function. So children, when we write f of x is equal to f of y, here we get x cube is equal to y cube, correct? X cube can be equal to y cube only when x is equal to y. Do you agree? If x is not equal to y, children, then obviously their cubes also will not be equal. Yes or no? X cube will not be equal to y cube. So under this condition, what we can write, when f of x is equal to x cube, f of x should be equal to f of y. That means if x cube and y cube are equal, then x and y should be equal. In that case, what we write, x is equal to y. So function f is 1 1, or it is an injective function, or it is injective, right, children? This function is an injective function. Very simple and easy, right? Did my children understand this, children? Yes, we have just proved that it is injective. Given a non-empty set x, we have a non-empty set x. Consider p of x, which is a set of all subsets. You know, children, if suppose, for example, I'm telling you, if you have x as 1 comma 2, okay, and p of x is set of all subsets what they have given, that means this p of x will contain every subset of this. It will contain null set, it will contain a set containing 1, it will contain a set containing 2. So all the subset. I hope this is clear. I'm just giving an example. So define the relation R in the set p of x for subsets a and b in p of x in such a way that, like as I told you, there are all the subsets under p of x. For those sets, we need to define a relation a comma b in p of x. A will be related to b only if a is a subset of b. This is the given condition, children. So we need to check whether this relation is an equivalence relation. Okay, if it has to be equivalence relation, now all my children know it has to be reflexive, symmetric, and transitive. So first, let us check whether this relation is reflexive. Observe this very carefully, children. Very important problem, because they have not given you the set. You need to try to understand what are the subsets and how to write the subsets. Under the subsets, we are going to do these operations. Clear? Now, see, you know that if you take a set A, okay, if you take a set A which belongs to P of X, consider set A belongs to P of X. You know, children, A is always a subset of A. True. In that case, A should be reflexive, right? So I can write A R B. It is really A R A. A is related to A. So it is reflexive. You take any set, a given set will be a subset of itself. That we already know. Yes. So this is reflexive. But consider, is it symmetric? Is it symmetric, children? Is it symmetric? Yes. Is this relation symmetric? Yes. Tell me, is this relation symmetric? If it is symmetric, tell me, when will be a relation symmetric? A relation can be symmetric only when, yes, when can be a relation symmetric, children? As a relation can be symmetric only when if A is related to B and B is related to A, correct? So if A is related to B, that means A should be a subset of B and B should be a subset of A. But consider, let's take a condition where A contains element 1 comma 2 and B contains element 1 comma 2 comma 3. In this case, observe this very carefully, children. I'm taking a typical case for you to understand it clearly. Here A is a subset of B, but is B a subset of A, children? Is B a subset of A? No, B is not a subset of A because all the elements of B does not belong to A. So this can happen only when A and B are same, Correct. A can be a subset of B and B can be a subset of A only when A and B are same. Otherwise, it's not. So it is not symmetric. This relation is not symmetric. I hope this is clear, children. Now let us go for the transitive condition. Now, is it transitive, children? Just observe and tell me, is this relation transitive? So if a relation has to be transitive, then if A is related to B and B is related to C, A also should be related to C. So observe this, if A is a subset of B, then take the condition B also is a subset of C. Do you agree that all the elements of A should also belong to set C? In that case, A also will be subset of C, children. Yes or no? Correct. In this case, what we can write? It is transitive. It is transitive. What is the reason, children? Because if A is related to B, yes, if A is related to B, then if B is related to C, okay, then A must be related to C. Yes, under this condition we write that this relation is transitive. You can notice that it is reflexive, not symmetric, but transitive. So it is not an equivalence relation. It is not an equivalence relation. Yes, children, I hope this is easy and clear. It is not an equivalence relation. So if a relation has to be equivalence relation, then it should be symmetric, reflexive and transitive. In this case, it is only reflexive and symmetric, so it is not transitive, so it is not a equivalence relation. I hope you have understood this question, children. This was an easy and simple question. Try to understand the concept of subsets. It will be very easy and simple. Find the number of all onto functions from set. The set is given as 1, 2, 3 till n to itself. So number of onto function from set to itself means from this set to the same set again. Correct, children? Yes, this is what is given in the question. So whenever you have to find the number of onto functions from a set to itself, always try to remember it will be just the arrangement, correct, of itself, right? It will be arrangement of n elements, I can tell. So number of all onto functions on this set, functions on this set will be the total number of possible arrangements in the set will be the total number of possible arrangement. And what is arrangement? You have already studied in grade 11, children. What do we tell? Total number of arrangement is nothing but total number of permutation of n elements. So I will write will be permutation. Yes, permutation is nothing but arrangement, permutations of n elements. And what is the permutation of n elements? Tell me, children. NPN is n itself. So the total number of onto functions from set to itself is n. So there are n number of onto functions possible. Yes, children, because whenever you have onto function, you have to find the total number of onto function for a set on itself. It will be the possible arrangements, correct? Possible arrangement is nothing but the possible permutations, which is NPN, which will be n. Easy and simple, children. You have easily solved question number 4 of your miscellaneous exercise. They have given set A. Okay, set A contains elements -1, 0, 1, 2. These are the elements in set A. What they have given. Set B is given as -4, -2, 0, 2. And they have given it clearly that f comma g tends to the function, that is f of x comma g of x, can be written as function A tends to B. That is, your domain is A and the codomain is B. Yes. Now f of x, function of x, is given as x square minus x, where x belongs to set A, and g of x is given as 2 times modulus of x minus 1 by 2 minus 1, where x belongs to A. So in this case, our f and G equal. And very important things, children, note down the element X both for f of X and G of X belongs to set A. And are F and G equal? That is a question. Justify your answer. Hint is given. One may note that two functions, that is f a to b and g a to b, should be such that f of a should be equal to f of a should be equal to g of a, where every element of a should belong to set A. These are called equivalents or equal functions. So they have clearly given the hint, children. So first, let us check for each and every element. Let us see what is f of minus 1, because minus 1 belongs to set A, correct? Yes. So when you're checking for f of minus 1, substitute, children, what do you get? Minus 1 the whole square. Yes, it is x square minus x, correct? F of x is x square minus x. Is the given function x square minus x, children? Yes. So it is x square minus x here. So when you're substituting under x square minus x, what happens? Tell me, minus 1 the whole square, minus 1 it becomes, correct? So what is minus 1 the whole square? Minus 1, children. And here, minus 1 the whole square, minus of minus 1, correct? So in that case, what do you get here? You get it as 1 plus 1, which is equal to 2. Now let us check what is g of minus 1. Tell me what is g of minus 1 here, children? G of minus 1 will be 2 times modulus of minus 1 minus 1 by 2 minus 1. So this is what is inside the modulus, what you get? Minus 1 minus 1 by 2 minus 3 by 2 becomes plus 3 by 2. So 2 gets cancelled. 3 minus 1, even here you're getting 2. So what is the conclusion we can write? I can write, observe this very carefully, because of f of 1 and g of 1 value we got, f of minus 1 and g of minus 1 value, we can write f of minus 1 is equal to g of minus 1, which is 2. So this is equal. Clear? Yes, children, is this clear? Now let us try to check for other numbers. What are the other numbers? We can check for f of 0, children. Tell me what happens to f of 0. 0 square minus 0, which is 0. What is g of 0? Tell me. What is g of 0? Again, 2 times modulus of 0 minus half minus 1. So what do you get here? 2 into 1 by 2, that is 1 minus 1, which is 0 again. So here what you can write, children, you can observe this clearly. F of 0 is equal to g of 0. So both values you're getting 0. Yes. Now let us check for other elements. What are the other elements present? We can check for f of 1. So if you're checking for f of 1, what happens? 1 square minus 1, which is 0 again. What is g of 1? It becomes 1 minus half is half, 2 times 1 minus half minus 1. So here what do you get, children? 2 times half minus 1, that becomes 1 minus 1, which is 0 again. And here you're getting f of 1 equal to g of 1. Yes or no? That is also 0. Now what are the other elements what you can check? F of 2. Check for f of 2, children, what you're getting? F of 2. It becomes 2 square minus 2. So that becomes 2. G of 2. What you're getting? G of 2, children? It is 2 times 2 minus half minus 1. So what do you get here? 2 minus half is 1, 1 by 2, that is 3 by 2. 3 by 2 into 2, it becomes 3 minus 1, which is 2. So here you are getting f of 2 also is equal to g of 2. Yes, children, in that case, you can observe f of minus 1 was equal to g of minus 1, f of 0 was equal to g of 0, f of 1 was equal to g of 1, and f of 2 is equal to g of 2. And according to the hint given in the question, when do you call it equal function? When for every element of A which belongs to set A, if f of A is equal to g of A, you can notice here f of minus 1 was equal to g of minus 1. Yes. F of 0 was equal to g of 0. Yes. F of 2 was also equal to g of 2, and f of 1 was equal to g of 1. In this case, we can conclude that it is an equal function. F and g are equal functions. Yes, children, what is the conclusion we are writing here? F and g are equal functions. Right, children? F and g are equal functions. Is that clear, children? Easy and understanding? So I hope this problem was clear. Let A be, they have given a set A which contains element 1, 2 and 3, and they are asking us the number of relations containing 1, 2, number of relation which contains 1, 2 and 1, 3 which are reflexive symmetric but not transitive. That means it should be reflexive, it should be symmetric, but it should not be transitive. Now observe this very carefully, children. The relation, required relation with minimum number of elements, required relation with minimum number of elements containing 1, 2 and 1, 3 can be written as R1. See, it should be reflexive, so I should write 1, 1 and I should write 2, 2 also. Since we have 3 also, I should write 3, 3 also. Yes. And it should be symmetric. In that case, 1, 2 should be there. 2, 1 also should be there. Correct. 3, 1 also should be there. 1, 3 also should be there. Correct, children? Yes. Now, observe this. Including all the 3 elements, what are the other relations we have not included? What are the other elements we have not included? We have not included, observe this very carefully, we have not included 3, 2 and 2, 3. Why, children? Why? Tell me. If you include 3, 2 and 2, 3, then this relation will become transitive. Right, children? It will become transitive. If you include these 2 elements, it will become transitive. Then it is not required for us. It should not be transitive. It should be reflexive and symmetric. And you can notice 1, 1, 2, 2, 3, 3. We have included this because it should be reflexive. It should be reflexive. Correct? That is given in the question. And we have included 1, 2, 2, 1, 1, 3 and 3, 1. What is the reason? Because we know that it should be symmetric. So if you include other 2 elements, it becomes transitive also, but we need not include them because we want it should not be transitive. So the number of relations possible which is reflexive, symmetric but not transitive is only 1. This is the only relation, right, children? This is the only relation. You can notice this is the only relation which is reflexive, symmetric but not transitive. So this is the only relation which is reflexive, symmetric but not transitive. Let us try to read these questions, and they are telling that let A be, they have given set A, and set A contains elements 1, 2 and 3. So we have 3 elements in set A. Then the number of equivalence relation containing 1, 2. So number of equivalent relation which contains 1, 2 is. See, children, when we are talking about equivalence relation, it should be reflexive, symmetric and transitive, right? We all know. So if the given relation is equivalence, if the given relation is equivalence, then this relation should be reflexive, symmetric and transitive, right? Now, the least equivalent set that can be formed using this. The least equivalent relation that can be formed using the element 1, 2 will be 1, 1 because it should be reflexive. So 2, 2 also should be there. Yes. 1, 2 also should be there. Yes. 2, 1 also should be there. Yes, children. Then what are the other elements we can include here? We can only include 3, 3. Yes, possible. Because if 1, 2 and 3 are present, 1, 1, 2, 2, 3, 3 should be present, right, children? So the least equivalence relation that is possible is 1, 1, 2, 2, 1, 2, 2, 1, 3, 3. But one more equivalent set if you want to form. Suppose you want to add elements. Here the only 2 elements which we have not added in the largest equivalent set is 2, 3 and 3, 2. Because if you add 2, 3, then to prove that it is transitive, you need to add 3. To prove that it is symmetric and transitive, you need to add 2, 3 and 3, 2 also. So in that case, if you're adding 2 and 2, 3, then you must add 3, 2. In that case, your equivalence relation will become 1, 1, 2, 2, 3, 3, then 1, 2, 2, 1, then 2, 3, 3, 2, right? And then, children, for transitivity, one more element, that is 3, 1 also should be added. Yes. And 1, 3 also should be added. Yes or no? Yes, possible. To prove it is transitive, you need to add that also. So in that case, you will add 1, 3 and 3 comma 1 also. Yes, to prove it is symmetric, you need to add. If you add 2 comma 3, you need to add 3 comma 2. And to prove transitivity, when 3 is there, you need to add 1 comma 3 and 3 comma 1 also. So in that case, now the number of equivalence relation possible for this will be 1 will be this and 1 will be this. So what is your right answer, children? It is total 2 equivalence relations are possible here. Yes or no? Only 2 equivalence relations are possible, and correct option is option B. Understood, right? The one equivalence relation R1 what you have taken just with the elements 1 comma 1, 2 comma 2, 3 comma 3, 1 comma 2 and 2 comma 1. We have not included 1 comma 3, 2 comma 3, 1, 3 comma 2 and 3 comma 1. But if you're including one of this, you must include the next 3 also. So the total number of equivalence relation possible for this is only 2. Is that clear and simple, children? We have easily solved question number 7 of your miscellaneous exercise. If you're understanding all these questions, please like, share and subscribe and share it with all of your friends so that even they can solve all these questions easily and score more in your examination.